Hello everyone, my name is Dongwei Jiang. Today I'll be presenting RATIONALYST, a novel approach for mining implicit rationales to improve process supervision of reasoning in large language models. This work was conducted by friends and colleagues from Johns Hopkins University and will be presented in ACL 2025. Let me start by talking about the focus of this paper. So what is reasoning and why it's crucial for LLMs? Reasoning is the ability to logically connect ideas, draw conclusions, and solve problems step by step. For large language models, strong reasoning capabilities are essential because it enhances accuracy, improves coherence, supports generalization, and increases interpretability. So we all know that reasoning is important. However, the issue is the reasoning steps current large language model generate may be incomplete because they may make logical leaps common in everyday communication that's found in their training data. Let me illustrate what reasoning leaps mean with this example from Harry Potter. Harry used magic outside of school, then he's punished. The implicit rationale that when someone breaks a rule, he will be punished is crucial for understanding this logical connection, but it's also left unstated in the original text. As a result, existing LLMs will have difficulty surfacing those implicit statements during the reasoning process, which can lead to flawed conclusions. To illustrate that, let's look at LLMs at work. When we ask an LLM about a person stealing food for their family, existing models might focus on the good intentions and conclude that they will be awarded, missing the crucial implicit rule about societal consequences for breaking the rules. And this is where our approach comes in. Our solution is RATIONALYST, which is a model trained on a vast collection of implicit rationales extracted from pre-training data to provide process supervision for reasoning. RATIONALYST works by making these implicit rationales explicit and using them to guide the reasoning process at inference time. For the example we have, RATIONALYST will help the model generate the complete reasoning. Although this stealing has good intentions, stealing from the store breaks the rule of society, so it should be punished. Now that you have understand the motivation, let me outline what I will cover next. For now, let's first talk about how is RATIONALYST actually used during inference. I'm going to talk about how to train this model in a bit. Let's take this math problem about Michael's golf balls from JSMK as an example. Given the preceding context, which includes the question and the partial reasoning trajectory, RATIONALYST first generates the implicit rationale. There are two steps in solving the problem. Let's first calculate the golf balls he lost after Tuesday. In parallel, an agent LLM, which can be an LLM trying to solve the problem, generates multiple candidate next steps for continuing the reasoning. And here's the key part. We use the rational R to score how well each candidate C aligns with the guidance provided. The correct step, after losing 23 on Tuesday, he had 15.8 minus 23 equals 25 golf balls, aligns well with the rationale about calculating golf balls lost after Tuesday. So it gets a higher score. We will then select the highest scoring candidate to continue the reasoning trajectory. This process continues iteratively. We update our reasoning trajectory with the correct step. After that, RATIONALYST generates a new rationale given the updated trajectory. It then guides the selection of the next reasoning step generated by the agent LLM. This iterative process ensures that every reasoning step is guided by appropriate implicit rationales, leading to more accurate final answers. Great. Now that you've seen how RATIONALYST works at inference time, let's dive into the next key question: how to mine a dataset of implicit rationales and train RATIONALYST. Our rational extraction process uses LLM to automatically extract implicit rationales from unlabeled data, which essentially is equals to using another LLM to generate training data for this one. We provide a carefully designed prompt showing the purple box, which instructs the LLM to identify implicit reasoning steps in the text or the unstated logical connections that bridges ideas and help predict what comes next. The prompt tells the model to look for logical leaps where important reasoning steps are assumed but not written out, and to add these implicit rationales using the special BOT and EOT tags. However, since those rationales are generated by LLMs, they can be noisy. We don't know whether they're useful or not, so we add a filtering mechanism based on future text perplexity. We would only retain rationales that significantly helps with predicting future text. If adding an implicit rationale reduces the perplexity of predicting future text, we would keep it, like the helpful rationale shown here about when someone breaks the rule, he will be punished. If a rationale has little effect on prediction, Like a relevant comment about Hogwarts magic being versatile, we discard it. This filtering mechanism ensures that we would only retain rationales that genuinely capture useful reasoning patterns. Once we have these high-quality rationales, we would use them to train rationalists. As shown in the diagram, the training process is straightforward. We start with llama 3 8 billion instruct as our base model and fine-tune it to become rationalist. The input is the preceding context, and we teach the model to predict the implicit rationales that should come next. So through supervised fine-tuning, rationalist learns the pattern. Given this context, what implicit reasoning step is missing? Now that we understand how to extract and filter rationales, let's move on to the evaluation section. Here are the extraction results across different datasets. We applied our rational extraction process to two main types of data sources. First, we use existing reasoning datasets like GSMAK and ECQA, which already contain structured reasoning examples. We also extract data from web-scale datasets like the pile, which includes various subdomains like Stack Exchange, GitHub, and others. The line chart shows the percentage of rationales retained after filtering across different datasets. You can see significant variation in retention rates, which quantifies the percentage of rationales upon perplexity-based filtering that are discussed in the rational extraction section. Reasoning datasets like ECQA retains 57% of generated rationales, while GSMAK retains 19%. For the pile subdomains, we see much lower retention rates, with Stack Exchange at 29.8%, being the highest due to its question answering format that naturally contains more reasoning content, while most other domains like the pile CC contains only 2.9% of rationales. The bar chart shows our final dataset composition. We extracted approximately 79K total rationales, with about 14K from reasoning datasets and 65K from the pile. The lower retention rates for most the pile subdomains reflect that web-scale data contains less explicit reasoning content, making rational extraction more challenging. However, the sheer volume of web data still provides substantial training material for rationalists. We test the benefits of rationalist on 7 reasoning datasets, comparing with the baseline without any supervision, rationalists without the pile data, and rationalists with full data, including the pile. The left chart shows the results across all 7 reasoning datasets. Adding web-scale rationales consistently improves performance. The right chart breaks down the improvements, and the improvements are particularly substantial for MMRU Pro, with a 5.7 gain on performance. This suggests that diverse rationales found in web-scale data help the model generalize to various reasoning scenarios. Finally, let's see how rationalist compares to other verification methods. First, a quick overview of the approaches. No supervision is our baseline without any verification. Process supervision evaluates each reasoning step during generation, and outcome supervision only checks the final answer. The agent model used here is llama 3 8 billion instruct. Looking at GSMAK results, no supervision gets 77.6 accuracy. Process supervision with llama 3 8 billion actually hurts the performance, while GPT-4 reaches 80%. Outcome supervision with llama 3 8 billion trained specifically on the training set achieves 79.2%. Rationalist hits 81.6, outperforming even GPT-4. We observe similar trends on ECQA. This shows that our specialized process supervision model beats general verification methods like GPT-4, even with much smaller model sizes. Let me summarize our key contributions. Our motivation was LLMs generating complete reasoning steps because they mimic logical leaps for everyday communication. Our solution involved extracting 79K implicit rationales from unlabeled text, training rationalist as a specialized rational generation model, and using it for process supervision during inference. Our results show an average 2.9% improvement across 7 reasoning datasets, outperforming even GPT-4 verification. For future work, we plan to scale up rationalist using stronger models like GPT-4 and llama 3 7 billion with larger datasets. And we also plan to perform better integration with test time compute and preference fine-tuning to make the training of rationalists better. We also reference parallel works that explore similar directions that involves rational extraction from unlabeled datasets. That's all for my presentation. Thanks.